Hello there and welcome back to the Sleep Science. You're not so much falling asleep tonight as falling inward, down into a place where marbles roll like waves, shadows bend without a source, and the rules you grew up trusting suddenly shrug and say, we were just suggestions. You're standing at the edge of the quantum rabbit hole and you probably won't survive this without a few mental cartwheels. That's fine. Physics is rarely fatal, it's just a little unsettling. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're at it, drop a comment with your location and local time. I'm always curious who's nodding off in the middle of the day and who's up at 3 a.m. wondering if electrons have favorite hiding spots. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're moving slowly, like you're underwater though no water surrounds you. In front of you, the floor begins to ripple. It's not a trick of light. This world allows reality to shimmer because here, particles and waves are not enemies. They're the same strange, cooperative thing. You bend to touch the surface, expecting your finger to meet solid matter, but instead, your hand slides through as though the floor was politely making space for you. This place was discovered in a way by accident. Around the year 1900, German physicist Max Planck, who you imagine here as a mustached tour guide, was trying to solve a pesky problem about how hot objects glow. Everyone expected a neat answer, but instead, Planck had to introduce something outrageous. Energy comes in tiny, indivisible chunks, which he called quanta. Historians still argue whether Planck truly believed this or just used it as a temporary patch. But either way, the patch stuck and changed everything. You take a cautious step deeper. The space here is dark but not empty, like a cinema screen before the film begins. You can feel the rules shifting. Imagine tossing a pebble into a pond, but when the ripples spread, the pebble also rolls along the shore at the same time. This is the first quantum trick your sleepy mind encounters, the dual nature of reality. A gust of something, wind or maybe probability, brushes your cheek. You think of a quirky story. In the early 20th century, some scientists still hoped all this weirdness could be explained away by hidden variables, like a magician with cards up his sleeve. But experiments, one after another, suggested that no, reality really does play dice. And these dice aren't even shaped like dice. You pause, feeling the quiet press in. The air smells faintly of ozone or maybe old chalkboard dust. You notice shapes floating in the dark, electron-like spheres, gently pulsing, as if deciding whether to be here or somewhere else entirely. When you reach toward one, it slips from your grasp, not by moving but by no longer existing here. That's the unsettling part. In quantum land, here, and there can be more like somewhere and everywhere. A particle's location is not fixed until it's measured, which is physics' way of saying until you look at it. The philosophical implications of this have fueled late-night arguments for more than a century, and there's no sign of them stopping. Up ahead, you spot something like a shimmering doorway. Beyond it lies a deeper, stranger realm. But as you move closer, you feel the need to slow down. There's a sense that the more you learn, the more fragile your sense of normal will become. Somewhere, a faint ticking echoes, a reminder of Planck's constant, that tiny number connecting the energy of a photon to its frequency. If the universe were a piece of music, Planck's constant would be the spacing between the notes, a kind of cosmic minimum. You grin despite yourself. This place feels both playful and slightly dangerous, like being inside a dream where the floor sometimes forgets it's supposed to be under your feet. You decide you'll keep going. After all, bedtime stories don't usually come with the risk of dismantling your concept of reality, so you might as well enjoy the novelty while it lasts. You step through that shimmering doorway and the darkness changes flavor, not literally, though you'd swear it now tastes faintly metallic on your tongue. Shapes sharpen. Edges hum faintly. It's as though you've entered a space where every rule has been rewritten in fine print, and you're just now learning to read it. Somewhere, Max Planck himself could be leaning against a lamppost, flipping a tiny coin in the air. Only it's not a coin, it's Planck's constant, the stubborn little number that's about to define your whole visit here. Roughly 626 times 10 minus 346, 626 backslash times 10 minus 346, 626 times 10 minus 34 joule seconds, so small that it's almost offensively inconvenient. You think of it like a mischievous gremlin whispering, "Oh, you thought energy was continuous, cute." Planck stumbled into this constant while trying to solve a problem called the ultraviolet catastrophe, which sounds like it should involve sunscreen but actually describes why hot objects should, according to classical physics, emit infinite energy in ultraviolet light. That didn't happen, obviously. If it had, your kitchen toaster would have doubled as a death ray. Instead, Planck realized that light energy had to be released in discrete packets, like coins dropping into a vending machine, rather than a smooth pour of syrup. Historians still argue whether Planck truly grasped what he'd unleashed, or whether he was just doing a desperate math patch job. Either way, his constant set the smallest possible scale for action in the universe. You can't chop it smaller, it's the atom of change. In this dreamlike hallway, you can almost see Planck's constant physically. It's stitched into the walls in glimmering golden threads, each one a reminder that the quantum world is built in steps, not slides. You brush your hand over them, and for a moment, your fingertips feel pixelated, as though reality here comes in discrete pixels of energy. There's a quirky little story you remember, a fringe theory from the 1920s that suggested Planck's constant wasn't constant at all, but might slowly change over time. No solid evidence ever backed it up, but you picture an alternate universe where tomorrow's Planck's constant is just a tiny bit different, and suddenly, your phone's battery thinks it's a sun lamp. As you walk, the golden threads converge ahead, braiding into a rope bridge over a chasm that seems bottomless. Below, faint glows flicker, waves of probability rising and collapsing like tiny fireworks. You take a cautious step onto the bridge, the planks creaking under your weight. You realize something. If Planck's constant were even a smidge larger, the quantum effects you're about to explore wouldn't stay politely hidden at the atomic level. They'd leak into your breakfast cereal, making spoons vanish halfway to your mouth. If it were smaller, quantum effects would shrink into irrelevance, and the universe would feel almost boring, clockwork predictable, no rabbits or holes to follow. A cold breeze drifts up from the chasm, and you wonder if it's carrying probability waves or just your own nerves. You can't see the far side yet, but you know Einstein is waiting there, ready to crash the party Planck started. He won't be happy about it, at least not at first. Before you move on, you kneel to peer over the side. The glow below is mesmerizing. It's a living reminder that reality's tiniest building blocks are ruled by this absurdly small constant, a kind of universal whisper that says, "This much and no smaller." You imagine explaining it to someone half asleep. They'd probably nod politely and think you been into the chamomile too hard. Still, you keep walking. Each step across the rope bridge is like moving along a number line, each plank another multiple of Planck's constant, counting out the rhythm of the universe in silence. You can't hear the beat, but you can feel it, soft, steady, unshakable. Halfway across, the air shifts again. You feel as though you've left the gentle introduction behind, and you're about to meet someone who's about to make this all even more complicated. The rope bridge delivers you onto a solid wooden platform that feels like it belongs to an old observatory. Round, domed ceiling overhead, the air tinged with warm brass and dust. A single spotlight falls on a figure leaning over a chalkboard. His hair is wilder than the sea in a storm, his mustache tidy enough to look like it has tenure, and his eyes have that far-off glint of someone who sees more than what's there. Einstein. He doesn't look up at first. You watch his hand scrawl numbers, arrows, and symbols in looping chalk strokes, each one landing with a confident tap. He's supposed to be the champion of smooth, logical physics, the clockwork universe that turns predictably forever. Yet here he is, in the quantum room Planck accidentally built, reluctantly sketching an idea that feels dangerous. The year is 1905, Einstein's miracle year, when he published 4 groundbreaking papers in one go. In one of them, he proposed something unsettling. Light isn't just a wave. It also comes in tiny packets called photons. This wasn't Planck's neat math patch anymore. This was an admission that the universe might truly operate in chunks. Historians still argue whether Einstein fully embraced quantum theory then, or simply tolerated it because it explained the photoelectric effect, an experiment where light hitting metal kicks out electrons. Classical physics predicted it would happen at any frequency if the light was bright enough, but nope, only certain frequencies could do the trick, no matter how bright the light. That was like saying you could yell as loudly as you wanted, but unless you used the right note, the glass wouldn't break. Einstein scratches a final equation on the board and steps back, noticing you for the first time. His brow furrows, as if he's trying to decide whether you're a curious student or a hallucination brought on by too much coffee. "You understand," he says in a soft accent, "I don't like this idea, but the evidence," he gestures at the board, "it is persuasive." There's a quirky historical tidbit here. Despite pioneering the concept of photons, Einstein spent decades arguing against the wilder implications of quantum mechanics. He was like someone who invented the first roller coaster and then said, "But we should really keep the track straight, yes." You glance around the observatory. The walls are lined with old brass instruments, each softly ticking, not measuring time but perhaps counting quantum events. A telescope points upward into nothingness, but when you peer through, you don't see stars. You see rippling patterns of light as though the sky is made of music. Einstein joins you at the telescope. "Light behaves as both a wave and a particle," he murmurs, almost to himself. "It is, how do you say, slippery." From the far corner, a strange sound draws your attention, like rain falling on paper. You turn to see beams of light hitting sheets of silver, electrons leaping off as though they'd been startled awake. It's the photoelectric effect in motion, a silent demonstration proving that light has this double life. You think of how disorienting this must have been for the early 20th century physicists, whose whole worldview was built on predictability. If light itself could break the rules, what else might be lurking in the shadows? Einstein walks you toward a heavy oak door on the far side of the room. The brass handle is cold under your palm. On the other side, he warns, you will see the experiment that unsettles everyone, even me. The door creaks open, and beyond it lies an open-air amphitheater under a velvet black sky. In the center stands a wide, rectangular panel with 2 narrow slits cut into it. You feel a strange pull, as if the air around you is holding its breath. "Go on," Einstein says with a wry smile. "Step closer. This is where reality begins to argue with itself." You step down toward the slitted panel, and the amphitheater feels suddenly too quiet, as though the universe has turned down the volume to let you hear the next part clearly. You descend the amphitheater steps, the hush so thick you could butter toast with it. The panel with the 2 narrow slits stands like a prop in a minimalist play, the kind where the actor is a photon with commitment issues. You can almost hear the audience of past physicists rustling in the dark, waiting to see if reality is going to behave or put on its clown nose and honk. A lamp flickers on behind you, no switch, just a quiet decision by the universe. A beam of light narrows to a single line, then softens into a gentle wash across the twin slits. On the screen beyond, dim bars appear, not 2 bright stripes as common sense would demand, but a delicate zebra of many lines. Bright, dark, like a barcode printed by a very patient ghost. This is the signature of interference, the telltale pattern of a wave splitting, overlapping, and arguing with itself about where to land. If you were rooting for Team Light is just a particle, sorry, your team's snack table is empty. You hear a whisper of history at your shoulder. Early 1800s London. Thomas Young stands before the Royal Society demonstrating that light makes interference patterns. That moment, 1801 by most accounts, was the mic drop for the wave theory of light. It didn't settle everything forever, but it was the kind of evidence that gets framed and hung in the living room. Historians still argue whether Young's experiment was truly novel, or whether Francesco Grimaldi's earlier work with diffraction deserves more of the spotlight. But the classic two-slit demonstration is Young's name tag at the party. You step closer and the pattern shimmers as if pleased to have an audience. Now the trick: you lower the light intensity so far that only one photon at a time creeps toward the slits, a lonely commuter catching the last train. One soft dot lands on the screen, another, and another. Each seems random, like confetti thrown by a bored toddler. But give it time, dot by dot, an interference pattern slowly materializes out of the chaos, as if the particle remembers a wave it once knew and is leaving breadcrumbs back to it. Joke number 1 lands gently in your mind. Apparently, even photons practice social distancing, yet still manage group projects better than most of us. You try to catch the photon in the act by peeking at which slit it takes. You place tiny detectors at the slits, the scientific equivalent of hidden nanny cams. Suddenly the pattern collapses, no more graceful zebra, just two fat stripes where you'd expect particles to go. Watching the path erases the wavy choreography, not watching lets the dance resume. The universe, it seems, does not simply perform, it performs for you depending on whether you stare. Creepy, a little, useful, untoldly. Great for bedtime. Well, you wanted interesting dreams. A quiet brass plaque near the screen ripples with later milestones. 1961. Electrons through a double slit by Klaus Jørgensen, proving matter itself, solid, suspiciously marble-like matter, can interfere like a wave. Electrons do the same eerie buildup, one by one, and yet collectively a wave pattern blooms. By the late 20th century, even buckyballs, soccer ball-shaped molecules of 60 carbon atoms, show interference. That's like tossing a whole deli sandwich at two doors and seeing mayonnaise fringes on the wall. Your second joke lands with a yawn. Somewhere, a lunchroom manager is filing a report, quantum vandalism, but delicious. Your hand grazes the edge of the slit screen. You feel a vibration, not mechanical, more like an itch in probability space. The floor under your feet remembers the golden steps of Planck's constant from earlier. Tiny actions click like beads on an abacus. You wonder if your shoes are leaving a wave function behind and decide not to think too hard. Your shoes are innocent. Mostly. This is where the philosophical traffic jam begins. If the particle behaves like a wave when unobserved, what counts as observation? Is it consciousness peeking through a keyhole or any interaction that leaves a mark? The lab doesn't care about your self-esteem. A simple detector is enough to wreck the interference. Measuring, and thereby entangling information with the system, changes the outcomes you see. Some physicists shrug and say, "Shut up and calculate," which, to be fair, is also how many people handle their taxes. Others spin off entire interpretations. Copenhagen, many worlds, pilot waves, theoretical airborne listings for reality's weirdness. In the dim bleachers, you glimpse a shadow in a rumpled suit. Richard Feynman leans on the railing and whispers that the double slit contains the only mystery of quantum mechanics. Not literally only, but emotionally only. The one that, once accepted, lets the rest slide into place. If you can handle a single particle interfering with itself like a restless cat arguing about which side of the door it wants, you're ready for the rest of the dream. A fringe-leaning tidbit wanders in like a stray cat. Thomas Young is said to have used a single human hair as a diffracting object, one hair building a whole rainbow fringe on a screen. The Hera's aperture lore shows up in old demonstrations. Whether that exact setup made the lecture is unclear, but the vibe fits the era. Physics powered by candlelight, razor blades, and a heroic tolerance for eye strain. You picture Young gently borrowing a hair, and you promise your own follicles they're safe. You run a what-if scenario. Suppose you install detectors but later erase the which path information before you look at the result. Now you're reenacting the quantum eraser experiments, spiritual cousins to Wheeler's delayed choice proposal. The interference pattern can be reconstructed in the correlations, as if the universe says, I can act like I never told you the secret if that's what you want. It's not time travel, it's bookkeeping in a language made of amplitudes. Still your third joke size. The cosmos is that friend who texts NVM after spilling tea and expects the room to unhear it. You step behind the panel and peer through one slit, then the other. The slits are twin eye holes in a mask the universe wears while it practices its lines. You think about how small changes to the setup, wider slits, shorter wavelength, stretch and squeeze the pattern like an accordion. Interference isn't mystical, it's geometry and phase. The mysticism creeps in when a single indivisible event contributes to a pattern that seems to require two paths at once. Your thoughts spiral to the micro-macro divide. In your kitchen, you never catch your toast interfering with itself on the way to the plate, even if toasted multigrain clearly contains multitudes. Decoherence is the bouncer here. Interactions with the environment, air molecules, photons, thermal noise, smear out the delicate phase relationships that make interference visible. At human scales, the wave function gets tangled with so many other things that the interference fringes wash out faster than you can say, "Where did my zebra go?" That's why your cereal spoon doesn't spontaneously split into a cloud of maybes. Quantum weirdness is fragile, a soap bubble that pops the second the room gets too crowded. You circle back to the screen and watch another slow build, order emerging from a drizzle of accidents. You can almost hear the probabilities humming, complex numbers twinning like strands of music. Somewhere, Einstein sighs again, dice rattling faintly in a cup. Somewhere else, Planck's constant taps its tiny foot to keep the beat. Historians still argue whether the language we now use, wave functions, operators, Hilbert spaces, was inevitable or just the particular clever poetry of a century's worth of problem solvers. Would an alien civilization have sung the same math, or found a different melody that fits the same tune? A final demonstration. You slide the slits closed until there is only one. The interference vanishes, replaced by a single peak diffraction pattern, still wavy but less dramatic, like a polite ripple after a cannonball. Open both slits again and the full comb returns, a reminder that options, mere possibilities, change outcomes, even if you never pick one. It's the most quantum kind of FOMO. The paths you could take affect the path you do. As the amphitheater lights dim, you feel the narrative tug of where this is headed next. If a single particle can be two stories at once until you force a confession, what happens when the particle is something alive? Something with whiskers and a questionable attitude toward boxes? You rub your palms on your sleeves, hear the faintest purr of probability, and smile despite yourself. Whatever waits behind the next door, you suspect it has a nap schedule you will not enjoy supervising. You follow the purr. It's not the plush, warm kind that comes from an actual cat. It's more like a vibration in your ribs, a soft reminder that something is half here, half not. The amphitheater steps melt away behind you, replaced by a hallway lined with unmarked doors. You pass one, then another, until you reach the only one that seems to notice you back. The brass handle turns with almost no effort, as though the door has been waiting for you. Inside, the light is dim and greenish, like a laboratory in a film where the budget couldn't stretch to full-color bulbs. At the center of the room sits a table, and on the table, a plain wooden box about the size of a bread loaf. A key rests beside it. A card tucked under the key reads in looping script, Schrödinger's cat. You hesitate. Everyone's heard of it, right? You think of the pop culture version, a cat that's both alive and dead. That's the meme. But in truth, Austrian physicist Erwin Schrödinger never meant it to be a cute poster. In 1935, he designed it as a thought experiment to show how absurd it would be if quantum strangeness applied to large objects. Historians still argue whether Schrödinger's intent was mostly sarcasm, aimed at the Copenhagen interpretation championed by Niels Bohr, or whether he was honestly wrestling with its implications. Either way, the setup was theatrical. A sealed box containing a cat, a Geiger counter, a tiny bit of radioactive material, and a vial of poison. If an atom decayed, the detector would trigger a hammer that would smash the vial. Atomic decay is a quantum event. It happens randomly, and until you measure it, the atom exists in a superposition of decayed and not decayed. By the strict logic of quantum mechanics, the cat's fate would be entangled with the atoms, meaning that until you looked inside, the cat would be both alive and dead. You slide the key into the lock. It clicks softly, but you don't open the lid just yet. You imagine the cat, not a ghostly image, but a probability cloud with fur. Half its whiskers twitch, half don't. Somewhere in the blur, a tail both swishes and lies still. From the corner of your mind comes a quirky detail. Schrödinger himself was reportedly fond of cats in real life, which makes the thought experiment's use of one both more ironic and slightly more suspect. You picture him stroking a purring tabby while muttering about superposition under his breath, which would at least make the cat think he's attentive. You finally lift the lid. The box is empty. No cat, no poison, not even a scrap of fur. You realize, of course, that in this narrative, the cat was never really here. It's been padding along in the imagination of scientists for 90 years. What is in the box, though, is a small, spinning hologram of a cat flickering between alive and dead frames, like an old film reel with missing bits. Schrödinger appears, or maybe you imagine him leaning against the far wall. His eyes are bright but tired, and he gestures toward the flickering hologram. "You see the problem, yeah," he says. "For one atom, this is fine. For a cat, ridiculous. Yet mathematically, there is no line where quantum ends and classical begins." You nod. It's the question that still hangs over the field. Where exactly does the wave function superposition collapse into a single outcome? Is it the act of observation, interaction with the environment, consciousness? Decoherence theory suggests that the environment is constantly measuring everything, washing away interference patterns for large objects before you ever look. But no experiment has fully, cleanly drawn that border. You run your hand through the holographic cat. It fuzzes and splits like a bad TV signal. For a moment, you feel the oddest thing, that you are being measured by it. A wave function narrowing from infinite options to just one person in one place at one moment. A memory surfaces of a fringe experiment idea you once read about. What if you used a quantum event to determine whether to write a poem or not, then sealed it away unread for years? Would the poem exist in a superposition of written and unwritten until someone opened the envelope? Probably not in practice, but your brain can't help purring at the absurdity. You close the box again. The green light dims. In the quiet, you think about how the cat's legend has spread beyond physics into philosophy, pop culture, even casual conversation. Someone can say, it's a Schrödinger's cat situation, and even people who have never seen an equation will nod knowingly. At the far side of the room is another door, this one circular like a submarine hatch. The wheel in the center turns smoothly under your palms. You can hear a faint hum beyond it, like a mosquito that studied jazz. When it opens, you're greeted by a corridor lined with translucent tubes, each pulsing with tiny sparks. It feels like the cat's paradox has been distilled into pure rules now, stripped of fur and whiskers, ready to reveal another truth about the limits of what you can know. The corridor's translucent tubes pulse like fireflies that enrolled in engineering school. Each spark a small confession of what can and cannot be pinned down. You walk with your fingertips grazing the warm glass, feeling tiny tremors pass under your skin, a reminder that even your touch is an intrusion. You just left a room where a cat could be both, and now you enter a place where both is forbidden in a different way. You can't have perfect this and perfect that, no matter how politely you ask. A round alcove opens to your left, and inside it hangs a peculiar instrument. Half microscope, half lighthouse mounted on gimbals. A brass plaque reads, Heisenberg's thought experiment. You recognize the setup, the notorious gamma-ray microscope used in 1927 to dramatize the uncertainty principle. You crouch, peering through thick glass as if you might catch an electron doing something incriminating. The idea is simple enough to lull a sleepy mind. To see a tiny particle's position clearly, you need very short wavelength, high-energy light. But that punchy photon and bouncing off the particle kicks it, scrambling its momentum. Use gentler light and you won't disturb the particle as much, yet you blur where it is. Either the dot is sharp and the arrow is fuzzy, or the arrow is sharp and the dot fuzzes out. You don't get both. The universe, it turns out, has a strict 2-drink maximum for certainty. You straighten, and the corridor hums a soft chord, almost a lullaby with Planck's constant threaded through the melody. The rule you're feeling is usually written as deltax delta greater or equal to letter 210f2 backslash delta x backslash delta p backslash g backslash frac backslash h bar 2 deltax delta greater or equal to 2 letter 210f. Position uncertainty times momentum uncertainty is at least half of reduced Planck's constant. That same stubborn number you crossed a rope bridge with has sneaked into your pockets again, measuring how much fuzziness reality requires. What you're facing isn't a limitation of your gear, like a smudged lens. It's baked into the recipe. Mainstream history taps your shoulder. Werner Heisenberg, 1927, building on the matrix mechanics he'd sketched out 2 years earlier during a hay fever retreat on the North Sea island of Helgoland. Yes, seriously, he hid from pollen and invented a new language for physics. Consider that the most productive sick day in history. He later received the Nobel Prize in Physics in 1932 for the creation of quantum mechanics, and the uncertainty principle became its lullaby refrain, sung to every wide-eyed student trying not to panic. Historians still argue whether Heisenberg intended his microscope to be a literal measurement limit or merely an illustration of a deeper, operator-based truth. The math doesn't flinch, but the story you tell about why it holds still invites polite bickering over tea. You circle the microscope, and next to it a smaller case holds a snow globe. Inside, glittered electrons jitter in a glassy storm. A label whispers, prepare a state to sharpen X, watch P spray like confetti. You give the globe a gentle shake. The glitter spirals into a narrow band, your particle's position squeezed tight. But down at the base, a needle-tracking momentum swings wide, then wider. You squeeze one balloon and the other bulges. You grin, third-grade science fair style, and joke number 1 yawns awake. Maybe multitasking is impossible even for electrons. Good news for your inbox. Across the corridor, a long pane shows ghostly footprints, Gaussians marching in pairs. A docent's voice from nowhere, because of course, explains. The Heisenberg relation is actually one star in a constellation of uncertainty relations. Position momentum is the celebrity couple, but angular momentum, energy time, those cousins also demand polite distance. Energy time is the tricky relative. There's no time operator like position. But if a system lives only for a short time, the energy line broadens. That's why unstable particles don't have a single razor-thin mass but a spread. It's not that time is fuzzy, it's that brevity invites ambiguity, like speed dating but with Feynman diagrams. The corridor curls into a small reading room with chalk dust in the air. On a slate wall, the commutator x p equals I letter 210fx, p equals I backslash h bar x, p equals I letter 210f. It's the algebraic heart of the matter. Things that don't commute refuse to be measured sharply at the same time. If you switch the order of acts, first position then momentum, or the other way around, you get different results, like trying to put socks on after shoes. Joke number 2 knocks gently. Your laundry already knew operator algebra. You run a finger over the chalk. It squeaks. In the corner, a modest ski poster is tacked up. Heisenberg loved skiing, downhill thinking, uphill proofs. A quirky tidbit stretches its legs. On occasion, he played piano to unwind. Contemporaries joke that he practiced uncertainty in tempo. And that hay fever story, people still repeat it with a romantic twinkle, debating how much the sea air versus the stack of spectral lines nudged him over the finish line. Historians still argue whether the Helgoland Epiphany was the lightning strike, or just the moment the kindling finally caught. A doorway opens onto a balcony overlooking the amphitheater you left, where the double slit still dreams faint zebra stripes. Now, though, you notice a breeze of decoherence whispering across the seats, that environmental chatter which ensures big things don't keep quantum secrets for long. You think back to the cat, to its flickering both nests, and you feel the harmony. Uncertainty says you can't pin down conjugate partners at once. Decoherence says the world is nosy and ruins interference. The double slit says possibilities interfere, and Planck's constant taps time like a metronome. The band is tight, even if their lyrics are cryptic. You lean on the balcony rail and imagine an electron you want to trap in a tiny region, say, inside a quantum dot. The smaller the trap, small deltix / delta x deltix, the more its momentum spreads, large delta / delta p delta. So it rattles around, raises its ground state energy, and refuses to sit still. That's why atoms don't collapse into their nuclei, crowd an electron too closely, and the uncertainty principle kicks up its heels, adding kinetic energy that props up the structure. The periodic table with its shells and chemistry glows quietly under this rule. If you've ever enjoyed table salt not imploding into a neutron star, you have uncertainty to thank. Joke number 3 pads by. Uncertainty, keeping your snacks from gravitationally self-destructing since forever. Back inside, a long bench hums to life with a slideshow of experiments. You see narrow slivers of light squeezing through optical cavities, atoms cooled to microkelvin in magneto-optical traps, laser beams sculpting uncertainty like a potter's hands. Squeeze states show up in gravitational wave detectors, where one variable's noise is reduced at the expense of its partner, a clever trade that lets LIGO hear space-time's faintest arias. This isn't just philosophy for insomniacs. Uncertainty budgets get written into lab notebooks like meal plans. A pamphlet flutters onto the bench titled Disturbance versus Intrinsic Fuzz. You flip it open. One camp emphasizes measurement-back action. Your probe shoves the system. Another points to the formal commutator structure. Even without literal kicks, non-commuting observables simply lack sharp joint states. Modern refinements, Ozawa's inequalities, weak measurements, nuance the old microscope parable without gutting the principle. Historians still argue whether Heisenberg's original wording overstated disturbance, or if that story was a stepping stone toward the deeper algebra he already knew. The debates are civil, caffeinated, and prone to blackboard karaoke. Past the pamphlet, a diorama shows a particle wave packet spreading with time. You watch a tight blob of probability inhale and exhale, its momentum spread dictating how fast it smears. Confinement today means wandering tomorrow. It feels like one more bedtime rule for your own thoughts. Try to hold them too tightly and they'll skitter. Give them gentle room and the center stays. You pause beside a glass case of humor artifacts, a novelty license plate reading deltix delta greater or equal to h/2, a bar coaster scrawled Heisenberg was here, probably, a fake speed ticket claiming, "Officer, I wasn't sure how fast I was going." Fringe? Maybe, but culture loves a principle that doubles as a punchline. At the corridor's far end, the tubes you first touched now run like parallel rivers of light, blue and gold. You rest your palm against one, and the glow splits subtly across your skin, as though your hand is both probe and participant. You can't avoid that. Measurement is a duet, not a solo. The tube's hum deepens, pulling you toward the next chamber. You think about how this uncertainty lullaby props up tunneling in stars, noise floors and amplifiers, the stability of matter, even the warmth of your pillow, 0-point jitters that never quite stop. The universe never sits perfectly still. It just hums softer when you're sleepy. A last plaque catches you with its quiet bravado. Certainty is cheap. Predictability with error bars, that's craftsmanship. You smile, eyes half-lidded, and let the principle fold around you like a blanket that never claims to be exactly the right size, just cozy enough and honestly labeled. The hatch ahead sighs open. Somewhere beyond, barriers are less barrier-ish than they look, and polite ghosts slip through stone. You step forward, letting the gamma ray lighthouse dim behind you, and breathe in a cooler air that smells faintly of granite and second chances. The air is cool enough to prickle your skin, but not unfriendly, like the breath of a cave that's been waiting centuries to meet you. The corridor ahead narrows into a rocky tunnel, its walls flecked with mica that catches the dim light. You brush your fingertips over the stone and feel a pulse, subtle, like a heartbeat buried far below the surface. At first, you think you've hit a dead end. A sheer slab of granite blocks the path, smooth and unbroken. You take a cautious step closer, and that's when you notice the shimmer, a faint outline of light just beyond the rock. Then, like someone hitting the fast-forward button, you're standing through the barrier on the other side. No cracks, no trapdoors, no plausible excuses. Quantum tunneling. You've just joined the ranks of particles that politely ignore the do not enter signs of classical physics. In the everyday world, a ball rolling toward a hill either has enough energy to climb over or it stops and rolls back. But at the quantum scale, the rules are fuzzier. Particles are described by wave functions that spread out in space, seeping into areas they shouldn't be able to reach. If the barrier is thin enough, part of the wave can make it through, and suddenly the particle, like you, exists on the other side without ever cresting the top. Mainstream history sets the stage in the 1920s. Physicists like Friedrich Hund and George Gamow recognized that tunneling explained alpha decay, how heavy nuclei spit out helium cores. Classically, the alpha particle doesn't have enough energy to escape the nuclear binding, but quantum mechanics says there's a finite probability it can appear outside anyway. That's why your smoke detector works. Its americium source releases alpha particles via tunneling, ionizing air and making the detector sensitive to smoke. Historians still argue whether Gamow's original tunneling paper got its warm reception because it solved a pressing nuclear puzzle, or because it was simply so weird that everyone wanted to see where it would lead. You take another step, and the world around you shifts into a half-laboratory, half-mountain vista. To your left, you see a line of glowing particles approaching a barrier, some bouncing back, some winking into existence on the far side. To your right, a model of the sun's core hums softly, because tunneling is the reason it shines. Protons in the sun don't have enough thermal energy to overcome their mutual electric repulsion, yet tunneling lets them fuse, releasing the light and warmth that's been making your breakfast possible for billions of years. A quirky tidbit catches your attention. In 1987, researchers observed electrons tunneling across an insulating barrier in Josephson junctions, superconducting devices that exploit tunneling for ultrasensitive measurements. These are so precise they can detect changes in magnetic fields thousands of times smaller than the Earth's. They're also used in quantum computing hardware, where tunneling isn't just a side effect, it's part of the logic. You crouch beside the granite slab, running your hand along its cool surface. On this side, you see faint ripples, imprints of your own probability wave leaking through. It's not like a ghost passing through walls, more like water soaking through paper when the fibers line up just right. Joke number one floats by. Barriers are just suggestions, like "do not touch" signs at a museum. The ground slopes down toward a glass floor. Below, you see a miniature tunnel junction, two metal plates separated by a thin insulating layer, electrons wiggling and warping through. A voice, Feynman again, maybe murmurs, "In quantum mechanics, anything not forbidden is compulsory." You can't tell if that's reassuring or vaguely threatening. You walk to the far end of the glass floor, where a display case holds objects that owe their existence to tunneling: flash memory, scanning tunneling microscopes, certain types of LED lasers. Another joke drifts past. Maybe you're just a highly advanced tunneling device for caffeine. Your gaze shifts to the horizon, where a mountain ridge glows faintly. As you watch, particles approach the mountain from both sides, some bouncing, some ghosting through as if the peak were only a rumor. You imagine a human-scale version, walking into a locked bank vault and by pure probability, finding yourself inside without touching the door. Security would call it magic. Physics calls it within the wave functions rights. Fringe theories sometimes flirt with the idea that macroscopic tunneling could happen, like a person suddenly appearing on the other side of a wall. But the probability is so absurdly small that it might as well be zero. You'd have to wait longer than the age of the universe for a realistic chance. Still, it's fun to picture. Late for work, you take one step and arrive at your desk, coffee in hand. Historians still argue whether indulging such thought experiments helps public understanding, or just makes everyone think physicists are auditioning for superhero franchises. You pause at a metal railing. Beyond it lies another barrier, this one shimmering like heat haze. Through it, you can see a spiral staircase leading upward into faint starlight. You know by now, you don't need a door. You take a step, and you're on the staircase, the barrier forgotten behind you. The stairs are narrow and cool under your bare feet, the air smelling faintly of ozone. You climb, each step like a beat in a slow metronome. You can hear the hum of spin now, the next quantum property waiting to be explained, particles twirling in ways that make even the cat's nap schedule seem reasonable. The spiral staircase opens into a space that feels both impossibly small and endlessly wide, a kind of particles dance floor. The air here is sharper, almost metallic, and you can hear a faint clicking, like tiny compass needles nervously tapping against glass. You realize you're surrounded by particles, but they aren't moving like billiard balls. They're spinning. Not spinning like a globe on a desk or a coin on a table. Spin in quantum mechanics isn't literal rotation in space. It's an intrinsic property, as baked in as mass or charge, but with a twist. Particles behave as though they have a built-in angular momentum, and this gives them magnetic personalities. Ahead, a silver contraption stands gleaming in the soft light. Two large metal funnels face each other with a narrow gap between them. This is the Stern, Gerlach apparatus, and you can almost see the ghost of 1922 in the air. Otto Stern and Walther Gerlach firing silver atoms through a non-uniform magnetic field, expecting a smooth smear of positions from randomly oriented spins. Instead, the beam split neatly into two distinct spots on a detector screen, up and down. Historians still argue whether Stern and Gerlach fully understood the quantum implications of what they saw, or if they simply marveled at the equipment's tidy refusal to produce a mess. But the result was the first clear proof of spin quantization. For certain particles, spin doesn't take on a continuum of values. It comes in discrete up or down, or for other particles, fixed sets of orientations. You step closer. The apparatus in front of you comes alive, firing tiny glimmers through the magnetic gap. Some fly upward, others downward, like polite party guests heading to clearly labeled floors. You imagine this as nature's version of a sorting hat, but instead of houses, it assigns magnetic alignments. Joke number one nudges in. At least this hat doesn't argue about your personality. Spin is a slippery idea. For an electron, up or down is defined relative to your chosen measurement axis. Change the axis, and the results shift. Even stranger, measure along one axis and then a perpendicular one, and the first result no longer predicts the second. Spins refuse to keep your notes straight. It's as though every new measurement politely erases the last decision. In the far corner, a table holds a model of an electron as a small sphere with a fuzzy, glowing aura. This is for your sleepy brain's benefit, because the real quantum description doesn't need physical spinning to create spins effects. It emerges from the mathematics of quantum fields, specifically the solutions to the Dirac equation for fermions. But imagining a little cosmic top isn't entirely useless. It helps explain why spins interact with magnetic fields. a quirky tidbit catches your attention. In 1924, Wolfgang Pauli introduced his exclusion principle partly to explain electron arrangements in atoms. The rule: no two fermions particles with half-integer spin can occupy the same quantum state. This is why electrons pile into orbitals the way they do, shaping the periodic table. Without spin and Pauli's principle, chemistry, and by extension, breakfast, wouldn't exist. On a glowing screen, you watch visualizations of spin of particles processing in a magnetic field, tracing slow cones in space like tipsy dancers trying to keep a candle upright. Larmor precession, the name whispers. The rate depends on the particle's magnetic moment and the field's strength, principles harnessed in nuclear magnetic resonance, NMR, and magnetic resonance imaging, MRI. The thought that your doctor's MRI machine is basically a giant spin orchestra briefly makes you want to applaud in a waiting room. A second joke strolls in, uninvited. Technically, you've been inside an MRI every time you've been in a department store security gate. Those tags sometimes exploit similar resonance tricks, just without the dramatic 3 Tesla soundtrack. You walk past a set of nested rings, models of particles with different spin values. Photons with spin 1, electrons with spin A, the Higgs boson with spin 0. Above them, a banner reads, "Spin determines statistics." You remember the distinction. Fermions with half-integer spin obey the exclusion principle and Fermi-Dirac statistics. Bosons with integer spin can pile into the same state, leading to marvels like Bose-Einstein condensates, where whole clouds of atoms act as a single quantum wave. Historians still argue about whether the term spin was a linguistic misstep. Early physicists borrowed it from classical rotation, even though quantum spin isn't a literal spin. But the name stuck, and so did the mental image of particles as tiny tops twirling in unseeable ways. A nearby console invites you to measure a particle's spin along 3 axes in a row. You try it. The results seem random, but when you repeat the same axis measurement twice in a row, the second time matches the first. Change the axis in between though, and the memory resets. Spin isn't stubborn, it's opportunistic, adopting whatever state your measurement demands. Joke number 3 sighs contentedly. Quantum particles would make terrible alibis. They can't keep their story straight under questioning. You glance back at the stern Dirichlet device, now slowing its stream. The sorted spots on the detector screen fade, replaced by a single shimmering doorway. Through it, you can see filaments of light stretching across impossible distances, like the faint glow of telephone wires in a fog. Spin has set the stage for one of quantum mechanics' most famous and unsettling tricks: entanglement, where measurement outcomes are linked across space in ways that make even Einstein mutter about spooky action at a distance. You take a deep breath and step forward. The air changes, warmer now, as if you're stepping into a shared conversation that started long before you arrived, and one that will continue long after you leave. You emerge into a landscape that feels both infinite and intimate, like the inside of a snow globe with no glass. Threads of light stretch in all directions, pulsing gently, some taut, some swaying as though in a breeze you can't feel. Each thread is anchored at 2 ends, but the anchors are far apart, sometimes farther than you think apart should even mean. Welcome to entanglement. Somewhere above you, a quiet voice that might be Einstein's mutters, "Spuckhaft Fernwerkung," spooky action at a distance. You look up and almost expect to see him shaking his head. For all his early role in quantum theory, Einstein was never comfortable with this. Along with Boris Podolsky and Nathan Rosen, he crafted the 1935 EPR paper, arguing that quantum mechanics must be incomplete because it allowed particles to remain mysteriously linked, even when separated by vast distances. You walk along one of the glowing threads, noticing how it hums in your presence. On your left, a small sphere flickers spin up. On your right, its partner sphere, impossibly far away in the thread's geometry, flickers spin down. If you change one, the other changes instantly, no matter the gap. It's not that information travels faster than light. It's that the pair's shared state was always a single thing, stretched out like a scarf. Measure one, and you define the whole scarf at once. Historians still argue whether Einstein's discomfort was purely about faster-than-light implications, or also about the philosophical unease of a theory that doesn't tell you what's really happening between measurements. Ahead, two stations sit across from each other. A particle approaches each. They're measured at angles you choose, and your sleepy mind remembers the 1960s experiments of John Bell. His inequalities gave a way to test whether local hidden variables could explain quantum correlations. Decades of careful experiments, Aspect in the 80s, Zeilinger in the 90s and beyond, have consistently shown violations of Bell's inequalities. Nature's verdict: entanglement is real, and no local hidden variables can fully explain it. You pause beside one of the measuring stations, watching as entangled photons hit detectors on opposite sides. The results pile up, matching or mismatching more often than any classical scheme would allow. It's as if the photons are whispering to each other through a channel no one else can tap. A quirky tidbit surfaces. In 2017, a team used starlight from opposite sides of the sky to choose measurement settings for a Bell test, minimizing the chance that any shared cause could influence both detectors. If any conspiracy predetermined the results, it would have had to start hundreds of years ago, when those photons left their stars. The universe, it seems, would have to be committed to the bit for a very, very long time. You step onto a narrow bridge of light spanning a gulf of darkness. Below, countless threads stretch into the deep, their ends glowing faintly where particles share their fates. Some are short, close connections inside an atom. Others are unimaginably long, linking regions that could never communicate by ordinary means in a reasonable time. Joke number one drifts in. It's like the universe's most overbuilt friendship bracelet collection. On the far side of the bridge, you find a table set with three objects: a pair of sunglasses, a crystal prism, and a small brass key. You put on the sunglasses and suddenly see hidden patterns in the threads, polarization entanglement, where two photons share linked orientations of their electric fields. Tilt the prism, and you watch time-correlated flashes from energy-time entanglement experiments, each pair perfectly synced. The brass key does nothing obvious until you notice the threads rearranging themselves into complex loops, multi-particle entanglement, the kind used in quantum computing and error correction. Historians still argue about the interpretation of what you're seeing. Is entanglement a physical connection in some unseen medium, a purely mathematical reflection of shared information, or just the universe refusing to commit to one reality until forced? Interpretations like many worlds sidestep the spooky part by saying no instant change happens. You just find yourself in the branch where your measurement matches the partner. Copenhagen says stop worrying and enjoy the statistics. Relational quantum mechanics asks, why assume anything exists outside relationships between observers? In the distance, you notice a faint shimmer, two glowing points, then three, then an entire lattice of entangled states forming a net. This isn't just pairwise, it's the stuff that makes quantum teleportation possible. You realize the next path is lit by that possibility, sending information across space without moving the thing itself. A second joke takes shape. You've never seen long-distance relationships work this well without at least one awkward holiday dinner. Before you leave, you touch one of the threads. It pulses brightly, and somewhere far away its partner must have flared too. You feel the tiniest pull, not physical but the tug of a shared outcome snapping into place. It's both intimate and alien. A fringe tidbit whispers in. Some researchers explore entanglement harvesting, using particle detectors to pull correlations from the quantum vacuum itself. If space is already teeming with subtle connections, maybe entanglement isn't something we create, but something we uncover, like brushing dust off a spider's web that was always there. The bridge ends at an archway woven from threads, each strand humming at a slightly different pitch. Through it, you glimpse the shimmer of the teleportation chamber, bright rings of light stacked like ripples in a pond. You step through, feeling the hum rise in your bones, as if the next idea is already rearranging the probabilities around you. Joke number 3 lands as you go. Finally, a way to send yourself across the world without paying for extra luggage. The archway deposits you into a chamber that feels like the inside of a ripple frozen mid-wave. Rings of light hover in the air, stacked and slowly rotating, each shimmering with a faint, silvery interference pattern. The space hums with quiet precision, like a room full of chess players who never speak but somehow know each other's moves. Welcome to quantum teleportation. You turn slowly, taking it in. This isn't the sci-fi beam-me-up version that ships your atoms across space. Instead, it's the stranger, subtler kind, using entanglement to send information about a quantum state from one place to another without the state itself ever traveling through the gap. At the center of the chamber, 2 glass spheres float on opposite sides of a black pedestal. A faint thread of light connects them, an entangled pair, already whispering to each other across the room. A voice calm, precise, maybe Anton Zeilinger's, explains. In 1997, his team in Innsbruck demonstrated quantum teleportation for the first time with photons. They created an entangled pair, kept one photon B at the receiving end, and sent the other A to interact with a third photon C, carrying the unknown state they wanted to teleport. By performing a joint measurement on A and C, they collapsed the entanglement in such a way that photon B, far away, took on the exact state C had held. Historians still argue whether teleportation is the best word. It doesn't move matter, and it always requires a classical communication channel alongside the entanglement link. Still, it's hard to deny the elegance. The state is destroyed at the source and recreated at the destination, as if the quantum property simply hopped across reality's ledger. A console beside the pedestal invites you to try. You place a small glowing particle into a holder labeled unknown state. The pedestal hums. The rings of light overhead begin to spin faster, blurring into luminous hoops. The particle in the far glass sphere flickers, and when the light settles, it now carries the state you placed in the holder. The original is gone, as if it never existed here at all. Joke number 1 drifts in. Congratulations, you've just invented the world's most expensive way to move a coffee order across the room. You step around the pedestal, looking closer at the entangled threads feeding into each sphere. This isn't just about parlor tricks. Teleportation is part of the toolkit for building quantum networks. Imagine a future quantum internet, where information travels securely using entanglement swapping to link distant nodes. You watch a holographic diagram unfold above the pedestal, showing how 2 separate entangled pairs can be connected. Perform a joint measurement on one particle from each pair, and the 2 unmeasured particles become entangled themselves, even though they've never interacted. A quirky tidbit makes you smile. In 2020, researchers achieved quantum teleportation across a 44-kilometer optical fiber network in the US, a practical test of what could someday become a sprawling quantum communication grid. Not bad for something that, 30 years earlier, many physicists thought would stay a theoretical curiosity. The rings of light shift to display other demonstrations, teleporting atomic states, teleporting between solid-state qubits in superconducting circuits, even experiments with light and matter hybrids. The process is always the same: entanglement plus joint measurement plus classical signal. Without all 3, the magic fizzles. Historians still argue whether this no cloning requirement, the fact that you can't keep the original state while making the copy, is a profound security feature, or just a technical limitation dressed as a virtue. Either way, it means quantum teleportation is perfectly suited for secure communication. The act of intercepting the process destroys the state. You move toward a tall mirror in the corner. It's framed by the same glowing threads you saw in the entanglement hall. You expect to see your reflection, but instead, there's a faint outline of another you in another chamber, holding a particle that mirrors yours perfectly. For a moment, you feel a subtle swap, the sensation that the pattern of you, the sum of your microscopic states, could step through without your atoms budging. Joke number 2 lands. Unfortunately, your socks would still be mismatched at the destination. Teleportation can't fix fashion errors. You walk along the outer edge of the room. Display cases hold artifacts of the field. A replica of the 1997 Innsbruck photon source, fiber optic spools from the earliest metropolitan-scale experiments, and a mock-up of the quantum repeater, devices that chain teleportation links together over long distances without breaking the fragile entanglement. The final display is a glowing cube with 3 labeled sides: entanglement, measurement, and classical channel. A placard explains that no matter how advanced the experiment, these 3 pieces are the recipe. Remove anyone and teleportation is impossible. The cube spins slowly, and you realize it's also a subtle exit sign. The only way forward is to accept all 3 and step into whatever they lead to next. Through a narrow doorway at the edge of the chamber, you glimpse a deep blackness, punctuated by faint glimmers. Not stars, something more restless. You realize with a small shiver that you're about to walk into a place where empty space is a misleading name. Joke number 3 trails after you. Quantum teleportation is proof that even the universe loves a good magic trick, provided you bring your own instructions and a landline. You step through the narrow doorway and are immediately swallowed by blackness, so complete that for a heartbeat you think you've closed your eyes. Then slowly, the darkness begins to breathe. Not literally, but in a way that makes you aware it's alive with something. Tiny specks wink in and out of existence like fireflies with stage fright. Threads of faint blue light spiral lazily, dissolve, and then return, never quite in the same place twice. Welcome to the vacuum, which, inconveniently, isn't empty. Your feet find solid ground, a glassy platform that feels like walking on frozen smoke. Beneath it, the blackness is restless. You recall what textbooks sometimes hide between equations. Even in empty space, the quantum fields never sit completely still. They jitter with zero-point energy, the unavoidable background hum that comes from the uncertainty principle itself. A deep, warm voice, perhaps Paul Dirac's, or just your imagination borrowing his British composure, begins to narrate. In classical physics, a vacuum is nothing. In quantum field theory, it is the lowest energy state of a field, yet not zero energy. Every particle type has its own field spread across space, and in the vacuum, those fields still fluctuate. Historians still argue whether calling it empty space was ever a good idea. After all, quantum electrodynamics predicts that these fluctuations have measurable effects, like the Casimir effect, which Dutch physicist Hendrik Casimir predicted in 1948. Place 2 uncharged metal plates very close together in a vacuum, and they feel a tiny force pulling them together. Not magic, just the quantum fields outside the plates having slightly different fluctuations than the ones between them. In 1997, precise experiments finally measured it directly. A glass case on your left holds a scale model of such a setup, 2 perfect plates, only a few micrometers apart, hovering in a transparent cube. A faint mist dances between them. When you lean in, you can hear the tiniest static hiss. A quirky tidbit surfaces. In 1948, Casimir was actually working on colloids, mixtures of tiny particles suspended in liquid, when he stumbled into the calculation that led to the effect. His aha moment came not in a dark vacuum lab, but over what must have been a very distracting cup of coffee. You wander further into the blackness. Here and there, holograms bloom. One shows the Lamb shift, another subtle fingerprint of vacuum fluctuations, first measured in 1947 by Willis Lamb and Robert Rutherford. It's a tiny difference in the energy levels of hydrogen's electron orbits, explained by interactions with the jittery vacuum's electromagnetic field. Without accounting for it, predictions and experiments would refuse to shake hands. Joke number 1 drifts in. So the universe's background noise is basically the cosmic equivalent of your neighbor's TV bleeding through the wall. Underfoot, the glass platform changes. Now it's a kind of observation deck. You look down and see pairs of ghostly particles appearing and annihilating in flashes, particle-antiparticle pairs, virtual but real enough to briefly influence the world before disappearing back into the foam. These virtual particles are part of the math of field interactions. They're not permanent residents, but they still leave fingerprints, like ripples on a pond that vanish yet prove the stone was thrown. Historians still argue about how literally to take the particles popping in and out description. It's a vivid teaching image, but in formal field theory, these are temporary disturbances in the underlying field, not physical billiard balls teleporting in. Still, the picture sticks because you can see it here. Ahead, a door-shaped shimmer hangs in the air, framed by equations. The most prominent is a vacuum E/text vacuum, the vacuum energy density, a number that, when calculated naively, comes out absurdly huge compared to the actual observed value inferred from cosmology. This mismatch, the cosmological constant problem, is one of the deepest puzzles in physics. Why is the vacuum's energy so small compared to quantum predictions? And yet it's not zero, because dark energy, the thing making the universe's expansion accelerate, seems to act just like a tiny vacuum energy. You pass a model of the early universe, a glowing sphere expanding rapidly in a dark void. A sign explains how inflation theory uses vacuum energy to drive exponential expansion just after the Big Bang. It's all tied to the idea that nothing is really something, and sometimes that something is powerful enough to reshape everything. Joke number 2 slides in. Apparently, the universe was built on a startup budget of empty space and a very aggressive growth strategy. You drift toward the far wall of the chamber, where the darkness feels thicker, almost syrupy. This is where quantum vacuum meets strong fields, regions near black holes, or in experiments with intense lasers, where fluctuations can become real particles. The Schwinger effect predicts that a strong enough electric field could rip virtual pairs apart before they annihilate, turning them into actual matter. It hasn't been observed directly yet. The fields required are staggeringly high, but tabletop experiments are inching closer. A fringe tidbit whispers from the shadows. Some speculative theories imagine using vacuum fluctuations as an energy source, a kind of zero-point energy generator. None have ever worked, and most are the stuff of pseudoscience, but the idea persists in popular imagination, probably because free energy from nothing sounds irresistible on a slow Tuesday. The hum in the chamber deepens. You realize the platform is slowly carrying you forward toward an even more abstract idea, that these fields, ever present, ever shivering, are more fundamental than the particles they produce. The doorway ahead glows faintly, its threshold rippling like fabric in a gentle wind. Beyond it lies a place where particles stop being the main actors, and the stage itself takes center frame. Joke number 3 lands just before you step through. Turns out, nothing is not only something, it's busy enough to need a day planner. You step through the rippling threshold, and it's like walking into a room woven entirely from light and motion. There are no solid walls, only a vast, undulating expanse, stitched together with invisible threads that flex and shimmer when you move. You recognize it almost instantly, though you've never been here before. This is the quantum field quilt. Everywhere you look, the fabric ripples in gentle waves. In one corner, a vibration sharpens into a bright pinpoint, then dissolves, as if the field simply decided it had better things to do. You reach out, and the air pushes faintly back, not with the resistance of matter, but with the smooth elasticity of a trampoline stretched across the cosmos. A calm, professorial voice, maybe your own, on a good day explains. In quantum field theory QFT, particles are not fundamental. They are excitations, ripples of underlying fields that extend everywhere in space and time. There is an electron field, a photon field, a quark field, and so on. When you think you've found a particle, you've really just caught the field in a particularly lively mood. Historians still argue whether field theory was inevitable after quantum mechanics emerged, or whether it was a conceptual leap made possible only by the 20th century's cross-pollination of particle physics and special relativity. Either way, by the late 1940s, the marriage was complete. QFT could explain electromagnetism via quantum electrodynamics, QED, with precision so absurd it matches experiments to more than 10 decimal places. You wander across the quilt. The patches aren't square or neat, they're domains of different fields. The photon patch is restless, shimmering like sunlight on water. The gluon patch feels heavier, its ripples damped, as though it's always holding itself together under the strong force. The Higgs field is subtler, a barely perceptible tension everywhere, a background firmness that endows particles with mass. A quirky tidbit drifts in. When the Higgs boson was finally confirmed in 2012 at CERN, some newspapers dubbed it the God particle, a nickname Higgs himself disliked. The term came from a book title, not Divine Revelation, but it stuck because the particle that gives other particles mass doesn't exactly fit on a bumper sticker. In the far distance, you see regions where ripples from different fields overlap and lock together. Here, interactions happen, an electron passing a photon ripple, exchanging a tiny quanta of energy. The air tingles with invisible trades. Joke number 1 arrives quietly. The universe is basically a flea market of fields, each one hawking excitations to anyone who wanders by. You pause at a glowing embroidery hoop floating in midair. Inside it, a loop diagram spins slowly, a visualization of a Feynman diagram, showing how particles exchange virtual messengers when they interact. The lines aren't literal paths but bookkeeping for the math of field excitations. In QFT, the drama happens everywhere at once, with probabilities spread across all possible histories. The quilt beneath your feet starts to roll gently, carrying you toward a hill in the fabric. This is a visualization of a vacuum expectation value, a stable point where a field naturally settles. The Higgs field has one of these, and it's why mass exists. You can't turn it off without unraveling the entire universe. Historians still argue about whether it's meaningful to think of the Higgs field's value as tuned to allow life, or whether that's just survivorship bias dressed in cosmic awe. Halfway up the hill, you find a spinning wheel, each spoke labeled with a force: electromagnetic, weak, strong, gravitational. In QFT, 3 of these forces already live comfortably in the field framework. Gravity, stubborn as ever, refuses to play along. The wheel hums and then flickers, showing unification attempts, grand unified theories that try to weave all fields into a single patch of fabric. None has been fully stitched yet. Joke number 2 threads in. Apparently, the universe's quilt still has one square that Grandma refuses to sew until she finds the right color yarn. Near the crest of the hill, the fabric is taut, shimmering with equations. You brush your fingers over them, feeling the texture change with each term, mass here, coupling constant there. It's the same sensation you had earlier in the vacuum chamber, only now it's structured, almost civilized. A small alcove holds tools for measuring the quilt. One is a particle accelerator, represented here as a shining tunnel that loops back on itself like a golden ribbon. You step inside and feel the field surge, briefly birthing a flurry of excitations that scatter before your eyes. Another tool is a virtual probe, a screen showing renormalization in action, the mathematical trick that keeps QFT's infinite quantities from running wild, turning them into numbers that match experiments. Historians still argue whether renormalization is a profound physical truth about nature's scales or just a brilliantly effective hack to make the math behave. Either way, it works, and the quilt remains coherent. From here, you can see the next section of the landscape. Sudden, brief flashes where the quilt's ripples swell, create a pair of particles, and then vanish again. These aren't the stable excitations that form matter. They're fleeting, like sparks that burn out before they can light a candle. Joke number 3 lands as you head toward them. The quilt has moths, and they're made of probability. The hill slopes down toward a region that shimmers faster, its patterns less orderly. This is where virtual particles live, here and gone, borrowing energy from the field like a cat sneaking milk, always paying it back before anyone notices. You step forward, feeling the fabric thin under your feet, the waves quickening as if eager to show you their tricks. You angle down the quickening slope of the quilt, and the fabric starts acting like carbonated water. Tiny fizzing bulges of light swell and pop before your eyes. Each little swell is a maybe that almost becomes a thing, then thinks better of it. You feel a tickle along your arms, as though the air is dotted with soap bubbles you can't quite touch. The sign at the edge reads in tidy lab lettering, "Particles popping in and out." And yes, the quotation marks do a lot of work. You crouch by a bright fleck that swells like a heartbeat. In a blink, it splits into 2 faint motes, particle and antiparticle, dances a syllable of a dance, and then recombines, vanishing into the fabric with a soft SHH. You know the classroom version of this story. Virtual particles borrowing energy from the vacuum, paying it back fast enough that the universe looks the other way. Cute, helpful, and not quite the whole truth. In the rigorous language of quantum field theory, you're watching temporary disturbances, terms in a calculation, rather than little marbles teleporting in and out. But here in your sleepy science stroll, the picture is too vivid to dismiss. It's like calling latte art just milk equations. Technically correct, tragically joyless. Mainstream history rolls by on a glowing ribbon. Mid-20th century QED, Tominaga, Schwinger, and Feynman tames these fluctuations with renormalization, turning runaway infinities into predictions that match experiments to jaw-dropping precision. By 1947, the Lamb shift shows up in hydrogen spectrum, a tiny nudge from vacuum fluctuations. In 1948, the Casimir effect hints that empty space has opinions about metal plates. Measured, checked, framed, and mounted. You straighten and stroll through a spray of sparkles that feel like cool mist. Joke number 1 taps your shoulder. The vacuum is that friend who says they're doing nothing tonight, and then accidentally hosts a full-scale pop-up festival. A slender arch displays labeled vignettes, vacuum polarization, a charge surrounded by a swarm of short-lived pairs that slightly screen it. Self-energy, a particle briefly chatting with its own field and changing its effective mass. Running couplings, interaction strengths that drift with energy scale because the vacuum's foam responds differently at different zoom levels. You reach toward the vacuum polarization pane and see a cartoon electron cloaked in a fluttering cape of phantom dipoles. Your hand tingles, like touching a Van de Graaff generator made of maybe. Historians still argue whether virtual particles should be thought of as real in any everyday sense, or whether the only honest thing to call real is the final, measurable prediction, the scattering rate, the energy shift, the force on a plate. The diagrams help your brain build scaffolding. The math is the building. Either way, reality signs the receipt. You drift to a quiet overlook where the quilt thins into a star-speckled void. There, at the lip of gravity's amphitheater, a pale horizon curves, black hole country. You've read the postcards. In 1974, Stephen Hawking predicts that quantum fields near an event horizon make black holes radiate, very slowly, as pairs that form near the boundary get separated. One falls in with negative energy from the outside perspective. The other escapes as Hawking radiation. It is not literally a pair popping out of empty space with a cartoon boing, but the image helps your midnight brain. The deeper truth is that particle is observer-dependent. Different observers slice the field's vibrations into different notions of a particle. Still, the effects math sings the same tune. Quantum fields refuse to stay quiet, even when gravity shouts. Joke number 2 wanders in wearing sunglasses. Even black holes can't enforce a strict no-pet policy. The vacuum keeps sneaking in pairs. A side shelf holds oddities. A cloud chamber replica where tracks sometimes kink, as if briefly nudged by the vacuum's whisper. A tiny tabletop Casimir force meter, its plates hovering micrometers apart like patient clams. A stack of napkins allegedly doodled on by Feynman, loops, legs, and a ring of coffee, the original counterterm. Quirky tidbit time. Feynman famously hauled bongos to conferences. You imagine him tapping 4/4 while sketching a 2-loop correction, syncopation matching integrals, physics by rhythm. You pass a sign that reads delta delta H//2 isn't a coupon. It's there to save you from a classic pitfall. The energy, time, uncertainty relation isn't a get-out-of-jail card that lets you mint energy from nowhere. It's a statement about how sharply you can define a state's energy over a short lifetime. Virtual contributions don't break energy conservation. Conservation is built into the full amplitude, enforced at every proper vertex by delta functions and symmetry. The borrowing metaphor is a bedtime story that tucks you in without lying entirely. Historians still argue whether popular depictions, foam, froth, fleas on the back of spacetime, do more harm than good, or whether they're the necessary nursery rhymes that let non-experts sleep at all. Your vote tonight is nursery rhymes, but responsibly labeled. Ahead, a transparent table lays out the accounting, scattering cross-sections with and without loop corrections. The anomalous magnetic moment of the electron agreeing with experiment to parts in a trillion. Tiny vacuum whispers moving the last decimal place like a shy debutante. You think of how fragile these whispers are, and how loudly they speak when you build the right ear. Joke number 3 yawns and stretches. Your coffee budget fluctuates like a vacuum diagram, short-lived surges, then annihilation at the register. You listen as the chamber softens around you. The popping quickens, then spaces out like rain easing. Through a gauzy doorway, something steady gleams. A corridor tiled with qubits and interference fringes, signs pointing toward machines that think in sewer positions. But before you sprint into neon quantum computing, you feel the story slow, air thickening into a softer register, as if the vacuum itself is laying a blanket across your shoulders and dimming the lights by one more notch. The gauzy doorway parts, and you step into a corridor paved with something that looks like glass, but hums faintly underfoot like it's processing your presence. Patterns of light, ones, zeros, and something in between flicker beneath the surface. At the far end, you see machines glowing with a calm, icy blue, the kind of light that belongs to freezers and sci-fi control rooms. You've arrived in the realm of quantum computing. The air here is cold, and it smells faintly metallic, with a whisper of ozone. Hanging above you are copper pipes and shielding layers, descending into sleek chandelier-like structures, dilution refrigerators, the heart of many quantum processors, cooling qubits to temperatures just a fraction of a degree above absolute zero. The quiet here isn't emptiness, it's deliberate, an engineered stillness to keep the quantum states from shattering under the heat and noise of the ordinary world. You approach a transparent console. Inside, you see qubits, quantum bits, each a small island of possibility, capable of being 0 and 1 at the same time through superposition. Unlike classical bits, which must choose, qubits can hold both options until measured, weaving interference patterns that make certain outcomes more or less likely. Mainstream history shuffles into place. In 1981, physicist Richard Feynman suggested that quantum systems could simulate other quantum systems more efficiently than classical computers ever could. By the 1990s, algorithms like Shor's, for factoring large numbers, and Grover's, for searching unsorted databases, proved that quantum computers could outperform classical ones in specific tasks. Today, labs and companies race to tame decoherence, error rates, and scalability, the unglamorous details between a paper proposal and a useful machine. Historians still argue whether quantum supremacy, A term coined for the moment when a quantum computer solves a task no classical machine feasibly can, is the best name for the milestone. The term itself became controversial. The reality is more nuanced. Quantum advantage depends on the task. You place your hand over a qubit in the console. It flickers with interference fringes, reminding you of the double-slit experiment, possibilities woven into probabilities. But here, those patterns are not just a curiosity, they're a tool. The machine builds on them, amplifying the paths that lead to the answer and canceling the ones that don't. Joke number 1 clicks into your head. It's like cheating at a maze by exploring every path at once and quietly erasing the dead ends before anyone sees. You move along a bench line with different qubit technologies, superconducting circuits, ion traps, photonic qubits, spin qubits in silicon. Each has its own quirks. Ion traps use electromagnetic fields to suspend charged atoms in near-perfect isolation. Photonic qubits zip through optical fibers at light speed, shrugging off certain noise sources. Superconducting qubits use Josephson junctions to exploit quantum tunneling in circuits. Spin qubits harness the up-down states of electrons confined in tiny semiconductor dots. A quirky tidbit gleams from a display card. In 2019, Google announced its Sycamore processor completed a specific random circuit sampling task in 200 seconds, a task they estimated would take the most powerful supercomputer of the day about 10,000 years. IBM countered that a clever classical approach could shrink that gap dramatically. The back-and-forth continues, a reminder that bragging rights in quantum computing age faster than unrefrigerated milk. One wall holds a massive, glowing sphere with pathways of light crisscrossing inside. It represents entanglement, qubits linked so that their states must be described together, no matter how far apart they are physically. Entanglement allows quantum error correction, the magic trick that hides logical qubits inside networks of physical qubits, so that individual errors can be detected and fixed without collapsing the computation. Historians still argue about when and whether quantum error correction will make large-scale, fault-tolerant quantum computers practical, or whether hybrid systems will reign for decades. The engineering challenge is immense. Stable qubits are divas, decohering if you so much as look at them sideways. Joke number 2 floats by. If classical bits are obedient golden retrievers, qubits are cats, beautiful, independent, and prone to wandering off in the middle of your sentence. You pause before a hologram of Shor's algorithm unfolding step by step. The interference patterns glow brighter where the algorithm amplifies the right answers, dimmer where it cancels the wrong ones. In another hologram, Grover's search algorithm swirls like a whirlpool, drawing probability massed toward the target with each iteration. A fringe tidbit hovers nearby. Some researchers explore quantum annealing as an alternative, letting a system settle into its lowest energy state to solve optimization problems. It's not universal computing, but for certain tasks, it's like skipping the algebra and going straight to the answer key. You step toward the far side of the room. A sleek archway glows with faint, flickering images, many at once, overlapping, sliding past each other like transparent pages in a book. You recognize them as versions of you, each carrying the results of computations run in countless possible ways. The air on the other side smells faintly of rain and static. Joke number 3 lands as you put your hand on the archway. Maybe the next step is walking into a place where every possible you is already waiting, politely debating whose turn it is to exist. You step through the archway and the air changes immediately. It's heavier, almost syrupy, as if every possible version of it is trying to flow into your lungs at once. The light here is fractured, not in sharp shards but in soft overlapping veils. You see yourself, no selves, fanning out in every direction, each one walking a slightly different path across the same hazy floor. Welcome to the many worlds drift. The scene feels oddly quiet given the crowd. These other yous don't jostle or make noise. They move with the grace of reflections on water, each unaware, or politely pretending not to be aware of the others. This is Hugh Everett's territory, the 1957 idea that the wave function never collapses. Instead, all possible outcomes of a quantum event are realized, each in its own branch of the universe. Measure a photon's polarization, and both horizontal and vertical results occur, but in different branches. You just happen to find yourself in one. Mainstream history steps in with the usual split. Everett's proposal was largely ignored in his lifetime, only to be revived decades later by physicists intrigued by its mathematical simplicity. It removes the arbitrary collapse postulate of Copenhagen-style interpretations, but at the cost of multiplying realities like rabbits in spring. Historians still argue whether many worlds is a literal description of parallel universes or simply a mathematical metaphor that makes no experimental predictions beyond standard quantum mechanics. You can't test for the other branches, so in one sense, it's like debating the flavor of an invisible cake. As you walk, some of the other yous peel off into different corridors. One takes a left turn you didn't. Another stops to tie their shoe, which you're suddenly aware you could have done. The subtle tug you feel is the branching point. Moments ago, you were all the same, and now you're not. A glowing platform ahead invites you to try a demonstration. You place a cubit in sewer position and press measure. The platform ripples outward, and you see two branches form. On one, your cubit reads 0, on the other one. In your current path, you see only the 0, but you feel the symmetry of having been whole just before the split. Joke number 1 drifts by. In some universe, you press that button with your left hand and now have entirely different opinions about soup. You turn and notice one version of yourself stepping through a shimmering curtain where the cat from earlier, Schrödinger's notorious feline, is still flickering. In one branch, the cat is alive. In the other, it is. Both outcomes persist, each as real as the other. A quirky tidbit surfaces. Everett's daughter, Liz, once said she grew up knowing her father believed she lived in many worlds at once, a dinner table fact far stranger than most childhood stories. She later became a science fiction writer, arguably continuing her father's branching narratives in another medium. You wander toward a set of mirrors that face each other, creating an infinite regress. In each reflection, your expression is slightly different, as though each image is a different branch's version of you, all returning your gaze without recognition. Historians still argue about whether many worlds offers a clearer ontology. This is what really happens, or simply moves the mystery elsewhere, replacing "why does the wave function collapse?" with "why do we only experience one branch?" Decoherence explains why branches stop interfering with each other, but not why you find yourself in this one. A walkway curves upward into a balcony overlooking a vast web of glowing threads, each representing a universe's history. They all start tangled together in the early past, then separate, never touching again. You spot a few faint crossings, places where quantum interference between branches is mathematically possible but physically rare, like echoes from a sibling world. Joke number 2 sighs in. Somewhere out there, there's a version of you who made all the right life choices, and they still forgot to defrost the chicken for dinner. Below, a holographic map plays out a quantum experiment. An electron takes both paths in a double-slit setup, branching into universes for each outcome on the detector screen. You lean over the railing, watching the pattern emerge in one branch while, in others, it's slightly different. You realize the pattern of patterns itself could be infinite. A fringe tidbit shimmers in from the corner of the balcony. Some speculative cosmologists connect many worlds to cosmic inflations, multiverse. Though the two ideas are conceptually different, one emerges from quantum mechanics, the other from cosmology's geometry. The temptation to blend them is strong, but so is the risk of making a soup out of unrelated recipes. You head toward an arched exit, where the overlapping veils of light grow thinner. Beyond, the air looks calmer, but the gravity feels heavier, as though the next topic is something no one has quite solved, and it's been pressing down for a century. Joke number 3 lands as you reach for the archway. In some branch, you decided to stop here, but in this one, you're about to go looking for quantum gravity's elusive pillow. The archway exhales a faint gust of cool, dry air, carrying with it the subtle scent of chalk dust and mountain stone. You step into a vast, open plateau under a black sky spangled with stars. The ground is soft, not sand, not grass, but something that feels like densely woven thread. You realize you're standing at the seam between two worlds, one woven from the fabric of general relativity, the other embroidered with the delicate stitches of quantum mechanics. Welcome to the hunt for quantum gravity. Out on the horizon, two towering figures stand facing each other. One is built of smooth, sweeping curves, draped in a cloak of equations describing space-time as a pliable fabric, Einstein's general relativity. The other shimmers with jittering points of light, wrapped in the probabilistic haze of quantum field theory. Between them stretches a gulf, wide and stubborn. For nearly a century, no one has managed to build a bridge that both will accept. Mainstream history sets the scene. General Relativity, published in 1915, describes gravity as the curvature of spacetime caused by mass and energy. It's a theory of the very large planets, stars, black holes, the universe itself. Quantum mechanics, born in the 1920s, rules the very small atoms, particles, fields. Each theory has been tested to absurd precision in its own domain. But at extreme scales, inside black holes or at the Big Bang's first instant, they clash. Gravity resists being quantized like the other forces. Historians still argue whether Einstein himself ever truly believed quantum mechanics was complete, or whether his discomfort with its probabilistic nature fueled his decades-long search for a unified theory. You kneel and run your fingers through the ground. It's tangled, uneven. The thread that is spacetime here seems frayed in patches, as if probed too closely. At scales near the Planck length 1, 6 times 10 minus 351, 6 times 10 minus 35 meters, the smooth geometry of relativity is thought to give way to quantum foam, a restless churn where the concept of distance itself becomes fuzzy. Nearby, 3 paths lead into the dark. The first glows faintly with a looping musical rhythm, loop quantum gravity, which attempts to quantize spacetime itself, describing it as a network of discrete loops. The second path hums with high tension, string theory, where particles are tiny vibrating strings in higher dimensional space, gravity emerging naturally from their harmonics. The third path is shadowed and silent, various emergent gravity ideas, where gravity might not be fundamental at all, but arise from deeper microscopic principles, like temperature emerges from molecules. A quirky tidbit emerges from the shadows. In the late 1960s, when string theory first appeared, it was actually discovered by accident in an attempt to model the strong nuclear force. Only later did researchers realize one of its vibrational modes behaved exactly like a graviton, the hypothetical quantum particle of gravity. You walk the loop quantum gravity path for a while. Here, space is a network, nodes and links like a cosmic abacus. Volumes and areas come in discrete chunks, not smooth continua. Measuring the surface of a black hole in this picture would give you a finite number of Planck scale tiles. You take a step, and the ground clicks faintly underfoot, as though counting you in discrete intervals. Then you wander into the string theory path. The air thickens, and the ground seems to hum beneath your boots. You see the string's tiny shimmering filaments vibrating at countless frequencies. Extra dimensions curl around you like hidden corridors, too small to enter. Somewhere in this forest of oscillations, a graviton mode twangs softly, promising a bridge between quantum rules and the pull of space-time. Historians still argue which of these approaches, if any, will survive the next century. Neither has yet produced definitive, testable predictions that experiments can confirm. Joke number 1 strolls in. It's like watching two people argue about the best recipe for a cake no one has actually baked yet. You return to the plateau's center, where a single ladder rises into the black sky. Climbing it, you see a horizon line curve upward into the infinite, a black hole, its event horizon glowing faintly. The space around it feels warped, as though your thoughts themselves are bending toward it. Hawking's radiation theory flickers at the edge of your mind, one of the few ideas that merges quantum field theory with curved spacetime successfully, at least in principle. But even here, questions remain. What happens to the information swallowed by a black hole? Does it escape encoded in radiation, as some believe, or vanish forever? Joke number 2 lands. If black holes are cosmic shredders, the debate is whether they use confetti or delete forever. A fringe tidbit hums softly. Some researchers explore holographic principles, where our three-dimensional universe could be described by information stored on a two-dimensional boundary, a radical shift that might reconcile quantum mechanics and gravity. It sounds like science fiction, yet in certain cases, the math works startlingly well. From the ladder's top, you can see the far side of the plateau, another archway, this one wrapped in mirrors. Through it, you glimpse the faint image of your own eyes, staring back, as if to remind you that observation is itself a puzzle in quantum theory. The next chamber will press on the deepest question: does looking create reality or only reveal it? Joke number 3 follows you down the ladder. In some universe, quantum gravity has already been solved. It's just that the paper is stuck behind a really slow peer review. The mirror-wrapped archway swallows you like a drop of ink disappearing into still water. For a moment, there's only the sensation of being both still and in motion, your reflection stretching and folding around you like taffy. Then you step through, and you're in a round, dim room where every surface reflects you from a slightly different angle. Welcome to the measurement conundrum. The floor here is glossy and dark like obsidian. Hovering just above it is a single, softly glowing particle suspended in a lazy shimmer. It's in a sewer position, its position smeared out, its other properties humming quietly in probability space. All around the room are instruments, detectors, cameras, strange devices you don't recognize. Some are switched on, some idle. The question in the air is almost visible. When you measure this particle, what exactly happens? Does your act of observation collapse the wave function into one definite outcome? Or does the wave function always evolve smoothly, and you simply find yourself in the branch where the result matches what you saw? Mainstream history circles the particle like a polite ghost. The Copenhagen interpretation, Bohr, Heisenberg, and others in the 1920s, says quantum states are probabilistic until measured, and the act of measurement causes collapse. Everett's many worlds avoids collapse entirely, keeping the wave function's evolution intact. Objective collapse theories like GRW say wave functions spontaneously collapse at random intervals, independent of observers. And relational interpretations claim properties don't even exist except relative to something else. Measurement is just interaction. Historians still argue whether the Copenhagen view was meant as a deep truth about reality, or just a practical way to shut down late-night arguments and get back to calculating. You walk toward the floating particle. A panel slides out from the wall with 3 glowing buttons: measure position, measure momentum, and don't measure. You hover your hand over the first 2, feeling the weight of decision. Pressing one will nail down that property, but at the cost of smearing out the other. Not pressing at all leaves the particle in its delicate bothness. Joke number 1 rises unbidden. Measurement is basically the universe's version of pick a card, any card, except the deck changes itself while you're looking. In the corner, a small display shows thought experiments on a loop. Schrödinger's cat flickers in and out of view. Wigner's friend watches a measurement inside a closed lab, while you watch Wigner's friend, and the chain of who knows what spirals outward. You can almost hear Wigner sighing from some branch of reality. Where does the collapse happen, if at all? A quirky tidbit materializes beside the display. In 2019, researchers performed a variant of the Wigner's friend experiment using entangled photons and found results consistent with the idea that different observers can experience different facts about the same event. That doesn't settle the interpretation wars, but it does make the philosophical stakes feel a lot less hypothetical. You turn to the particle again and choose not to measure. Instead, you walk slowly around it. Its shimmer seems to follow your movement, not tracking you exactly, but adjusting, as though its probability cloud prefers you in certain places. You wonder if this counts as observation or just polite loitering. Historians still argue whether consciousness has any special role in measurement. Most working physicists say no, preferring to model the observer as just another quantum system. But a small number keep the question alive, poking at the edges where physics and philosophy blur. You notice another doorway, narrower, framed in brass. Above it is a single engraved word, decoherence. You've seen it before in hints and whispers. The idea that interaction with the environment, not human awareness, destroys the delicate phase relationships that allow superpositions to show interference. In this view, the wave function never collapses. It just becomes so entangled with its surroundings that the system behaves classically for all practical purposes. Joke number 2 hums in your ear. Collapse or not, the particle probably wishes you'd make up your mind so it can get back to its day. Before stepping through, you glance once more at the particle. For a fleeting moment, you imagine every possible outcome blooming outward like petals, each petal containing a different you, with different memories of this room. Maybe you've already pressed the button in another branch. Maybe you've never been here at all. A fringe tidbit flutters through the air. Some experiments in weak measurement allow physicists to extract partial information about a system without fully collapsing it. The results can seem strange, average values lying outside the normal range, but they offer a tantalizing peek at the in-between of quantum states. You put your hand on the brass frame. On the other side is a place where the border between the microscopic and the macroscopic starts to blur, where quantum weirdness steps shyly toward the everyday. Joke number 3 lands softly. You're about to find out just how far down the rabbit hole your breakfast cereal can go. You press your palm to the brass frame, and the room exhales you into a twilight lane where the air is warmer, thicker, slightly dusty, like an attic where someone's been storing whispers about reality. You're not in the land of electrons and single photons anymore. Not quite. But you aren't fully back in the chunky, classical world of cereal spoons and receipts either. You're in the hallway between. The mesoscopic realm, where quantum weirdness tiptoes into everyday stuff and then pretends it never left footprints. The carpet here looks ordinary until you crouch and see the fibers shimmering with tiny, out-of-phase ripples. A plaque on the wall in whimsical serif reads, "Decoherence did not kill quantum, it just taught it manners." You remember the lesson. Superpositions lose their delicate phase relations when they entangle with the environment. Air molecules, thermal photons, nosy neighbors named everything else. The trick to catching quantum outside the lab is to hush that environment. Cool it, shield it, baby it. In other words, parenthood. You pass a window and peer into a chamber where a droplet of liquid helium climbs the wall, thin as a whisper, superfluidity. At a few degrees above absolute zero, certain helium isotopes flow without viscosity, gliding through microscopic cracks like rumor through a small town. On another pedestal, electrons pair up in a lattice and waltz without resistance, superconductivity. You can almost hear the BCS theory hum, a chorus from 1957 where electrons form Cooper pairs via lattice vibrations and slip through the crystal without scattering. The magnet floating above a superconductor nods at you, politely levitating. Mainstream history plants a flag. 1986, the discovery of high-temperature superconductors by Bednors and Mueller, launching a frenzy to raise the transition temperature and turn liquid helium lab toy into practical tech. We're still chasing room temperature. Ambient pressure dreams with the enthusiasm of someone who swears the next coffee will fix everything. Historians still argue whether macroscopic quantum phenomena should be reserved for rigid, phase-coherent states like superconductors and superfluids, or whether any large-ish superposition counts, even if it's fragile and fleeting. Definitions stretch, egos obligingly follow. You keep walking. A glass case displays a soccer ball molecule, C60, Buckminster fullerene, floating between two narrow slits like a blasé parade balloon. The detector beyond blooms with an interference pattern. You would think something that big 60 carbon atoms playing hacky sack would pick a lane. But in 1999, teams demonstrated interference with C60. Later, even heavier organic molecules sauntered through and fringed the screen, their masses creeping into tens of thousands of atomic units. You can't help grinning. Joke number one leans on your shoulder. Apparently, molecules travel like influencers, always in superposition about which gate they're boarding. Ahead, a sleek workbench hums with optomechanics. A tiny mirror, micrometers across, sits on a cantilever inside a laser-lit cavity. The light's radiation pressure cools its motion toward the quantum ground state. Measurement back action and squeezed light finesse the noise. You watch a readout as phonons wink out like sleepy fireflies. The dream is to push that mirror, something with heft and edges, into a non-classical state, maybe even a cat-like superposition of positions, if only for a breath. Your mind hops to levitated nanoparticles, trapped in optical tweezers and coaxed toward delocalized states, and to superconducting microwave cavities where cat states of photons, two coherent states at once, are bred, fed, and used as qubits. The Yale-style cat qubits purr faintly in your memory, a callback to the feline that started this mess. At the next alcove, a coiled ribbon of niobium loops into a squid, superconducting quantum interference device, capable of detecting magnetic fields so small they should require a magnifying glass for reality itself. Two Josephson junctions stitch the loop. Phase coherence navigates flux like a bloodhound. You remember the tunneling corridor, polite ghosts slipping through walls, and recognize the same trick at work, now busy making precision technology sing. A wall-sized mural lights up. The LIGO interferometers, 4-kilometer arms measuring space-time, ripples from colliding black holes. Their sensitivity is so absurd that quantum noise from photons matters, so engineers inject squeezed states of light to reduce fluctuations in the measured quadrature. The double slits interference, Heisenberg's uncertainty, and Planck's metronome show up here as line items in an engineering budget, the universe's weirdness repurposed as a calibration curve. Joke number two twinkles. When the cosmos pings you from 1.3 billion light-years away, you tidy your quantum noise like a host fluffing couch pillows. You pause by a dim garden of living leaves, not metaphorical actual leaves bathed in cold green. A small note reads, excitonic coherence in photosynthesis. In some ultra-fast experiments, signatures suggest that energy transfer in certain complexes may exploit wave-like coherence, briefly guiding excitations along surprisingly efficient routes. Quantum biology? Maybe. The data are delicate, the conclusions delicately argued. Historians still argue whether these quantum beats in chlorophyll are smoking guns or just pretty smoke, artifacts of measurement or meaningful strategy honed by evolution. Next to the leaves, a miniature globe spins inside a dark box, ringed with birds. A postcard explains the radical pair hypothesis for avian magnetoreception. Entangled electron pairs in cryptochrome molecules might be nudged by Earth's magnetic field, changing reaction yields and giving migratory birds a built-in compass. The evidence is suggestive, not definitive. The models are brave, the birds unbothered. A quirky tidbit peeks out. Some labs found that weak radio frequency fields can confuse these avian navigators, as if you tuned their head compass to static and they politely blamed the weather. Your path threads past a glass-walled, quiet room, where a millimeter-scale drumhead in a dilution fridge rings in quantized steps. Outside, a plaque reminds you that macroscopic entanglement between photons, ions, even vibrational modes of solid objects has been demonstrated, though the bigger the system, the hungrier the environment gets. Decoherence is a gossip column that never sleeps. The only way to avoid scandal is to never leave the house, or, failing that, keep the house at 10 millikelvin. You turn a corner into what looks suspiciously like a kitchen counter. On it, a semiconductor wafer, a cheap laser pointer, a smartphone, and an MRI image pinned to a corkboard. The caption is endearingly blunt: quantum, but you already used it. Laser coherence underwrites telecom. Semiconductors rely on band structure and quantum tunneling. MRI sings spin's lullaby. Your phone's sensors, clocks, and cameras chew on quantum selection rules daily. You pick up the laser, tap the button, and a crisp dot appears. Interference's kinder, domesticated cousin in your palm. Joke number 3 takes an easy seat. You didn't bring quantum into your life. It moved in quietly and started paying the Wi-Fi bill. You can feel the micro to macro boundary now as a temperature gradient on your skin. On one end, everything is possible. On the other, everything is loud. Turn down the temperature, turn down the noise, and the wave function stretches its legs. Turn them up and it tucks itself in. There isn't a single magical line. There's a negotiation conducted in units of Kelvin, Pascal, and stray photons per second. A display of chalkboards rolls by with questions scrawled in sleepy loops. How big can we go? Cat states of superconducting currents. Massive molecules with fringes across meters. Levitated spheres in space, shielded from everything, their wave functions fat as a cloud. How alive can we go? Viruses in sewer position. Bacteria. Your eyebrows rise. Your ethics committee clears its throat. The chalk pauses on a sentence you've heard all night. Historians still argue whether the line between quantum and classical is an ontological cliff or a practical slope, whether collapse is real or just the story we tell when decoherence makes interference unnoticeable. You glance back down the corridor, collecting your callbacks like souvenirs. The cat who was both, the slits that were two, the spin that refused to keep notes, the entanglement bracelet that wouldn't break, the vacuum that never truly naps. Quantum has been here the whole time, humming behind chemistry, electronics, and sunlight on your face. But to see it wearing its sequins, you had to dim the lights and hush the room. Ahead, a low door opens into a paneled lounge, amber lit, filled with the soft murmur of human voices. Framed photos line the walls. Planck, Einstein, Bauer, Schrödinger, Heisenberg, Bell, Feynman, caught mid-gesture, chalk in hand, eyebrows arched. You realize where you're headed. The after-party of arguments, the cafe where interpretations pull up chairs and order strong coffee. You brush your fingers over the doorknob. The metal is warm, like a conversation already underway on the other side, 100 years long and still unafraid of another hour. You take a breath, remembering that crocodile dung sunscreen joke you never actually made. We'll save it for Egyptology night, and push gently. The lounge is the color of tea left to steep a little too long, amber and comforting with a bite. Carpets hush your steps. Low lamps pool light onto little round tables where legends lean in, sleeves rolled, chalk dust smudged like war paint. The air smells faintly of coffee, cigars, and the ozone of enthusiastic disagreement. You've wandered into the world's sleepiest shouting match, except no one's shouting. They're just deploying adjectives with surgical precision. At the nearest table sits Niels Bauer, spectacles low, hands drawing invisible diagrams that look a lot like your memory of the double slit. Across from him, Einstein toys with a pipe, brow arranged in that worried father look he wore whenever probability tried to flirt with destiny. Between them, like a cat that refuses to pick a lap, lies a single word: complementarity. Bauer's credo: no single classical picture can capture quantum systems. You need mutually exclusive views to tell the whole story. Wave and particle, yes and no. The room nods, your eyelids follow. Einstein takes a slow breath. God does not play dice, he murmurs, though he'd be the first to admit he'd said it in some form more than once. Bohr counterpoints with his famous half-playful volley, "Einstein, stop telling God what to do." You can feel the old Solvay 1927 electricity, history's most glamorous chalk fight, sparking gently over the table. That conference really did gather the titans: Einstein, Bohr, Schrödinger, Heisenberg, de Broglie, Born, Dirac. So many that the group photo looks like a physics Mount Rushmore stitched onto a single bench. Mainstream fact pins itself to the corkboard. In 1927 and again in 1930, Einstein wheeled out thought experiments to puncture uncertainty. Bohr parried each with careful rebuttals, invoking momentum carried by light and the finicky bookkeeping of measurement. No knockouts, just undefeated nuance. Joke number 1 curls up on the armrest. It's like the world's politest rap battle, with more integrals and fewer chain necklaces. Schrödinger drifts over, catless tonight, elegant and slightly exasperated by his own metaphor's afterlife. Verschränkung, he sighs, reminding you he coined the term for entanglement in 1935. At another table, a younger John Bell is drawing lines on a napkin, correlation bounds for any local hidden variable theory. He lifts the napkin, squints at it, then flips it and writes again. His 1964 paper will be the crisp hinge that lets philosophy swing into experiment. If nature keeps secrets locally, certain correlations simply can't be as strong as quantum mechanics predicts. But when the tests come aspect, in the 80s and many loophole-free ones since, the correlations break those classical limits with a shrug. Dice clatter softly somewhere. If reality's underlying story is local and per-written, it sure is hiding the plot twist well. Historians still argue whether Bauer's Copenhagen stance was ever a single coherent doctrine or a social contract to stop people from missing their train while arguing about metaphysics. The term, Copenhagen interpretation, came later, and what it names depends on who's writing the encyclopedia entry after midnight. A doorway opens to a smaller alcove where Louis de Broglie, looking like a prince caught sneaking into the lab, is sketching a pilot wave. In 1927, he proposed the idea. A particle is a definite little thing guided by a real wave in configuration space, a pilot setting its course. He shelved it after Copenhagen headwinds, but in 1952, David Bohm revived the program with clarity and steel, building a deterministic, non-local hidden variable theory that reproduces all the statistical predictions of standard quantum mechanics. You step closer, and in this corner, trajectories bloom across the two-slit screen, guided by a rippling wave. No collapse, no branching, just delicate, spooky coordination written into the guidance equation. Joke number 2 leans in conspiratorially. Pilot wave is the GPS that actually knows a back road, but sometimes insists you drive through a cornfield. A lanky figure at the bar taps a bongo discreetly. Feynman. He raises a glass, milk, root beer, nobody's quite sure, and says what he always says here: nobody understands quantum mechanics. He doesn't mean nobody can calculate, he means understanding, the kind that lets you build a single picture in your head and be done, keep slipping just out of reach. You nod like you understand not understanding. It's a warm blanket of honesty. On the wall, a chalkboard cycles through thought experiments like a slideshow screensaver. Wheeler's delayed choice. Decide whether to observe interference or which path after the photon passes the slits, and you'll still find the universe obedient but disconcerting. Quantum eraser variations wink and grin. Keep or erase which path information, and the fringes attend or demur accordingly. Somewhere near the coat rack, Karl Popper is grumbling about his own experiment, while the coats quietly decohere each other. You catch a whiff of ozone from a back shelf labeled Fringe and Folklore. The Pauli effect lives here. Rumors that whenever Wolfgang Pauli wandered into a lab, the apparatus would mysteriously fail. An apocryphal note says a piece of equipment once exploded across town when he arrived at the train station. Quirky. Oh yes. True. Historians still argue whether Pauli's bad luck aura is physics lore or just the universe making an inside joke at a theorist's expense. Also on the shelf, the horseshoe that Bohr supposedly hung over his door, defending it with the line, Of course, I don't believe in it, but I'm told it works even if you don't believe. Probably apocryphal, but it sparkles too perfectly to discard entirely. A quiet corner glows with new school debates. Objective collapse folks, GRW and friends, sip dark espresso and argue for a tiny, random physical process that knocks suppositions flat, especially for big systems. Many worlders, sprawled on a sofa like well-behaved octopuses, suggest we keep the math and accept that branches proliferate behind the scenes. No collapses, only decoherence and the inevitability of finding yourself somewhere. Cubists trade tasting notes, treating the quantum state as an agent's personal betting book for experience. Relationalists reply that properties are only ever between systems, not inside them. A lone pragmatist at the jukebox presses B52, mutters "shut up and calculate," and hums along. You drift to a map pinned across a cork wall, red string connecting eras and experiments. 1935, EPR sparks the locality fight. 1964, Bell hands the community a ruler. 1982, Aspect builds the testbed. 2015 and on, loopholes tight. 2022, the Nobel nods to Aspect, Closser, and Zeilinger. A century of conversation condenses into a handful of dates and a lot of coffee rings. Your fingers trace a route from the cat box to the telecom fiber, to a quantum repeater. Interpretation tangled with engineering more intimately than either side sometimes admits. Joke number 3 pads buy in socks. Interpretations are the phone cases of physics. Anyone will protect the math, but everyone insists theirs has the better grip. At the far table, someone raises the old, comfortable specter. Is the wave function real, ontic, or epistemic? Is it a physical field smeared over configuration space, or is it just a catalog of expectations, a tool for smart betting? A handwritten sign above the sugar bowl reads, "Please take only the sugar you can renormalize." You add 1 grain anyway. A projector hums, airing clips from the grand debates. Bow or packing, searching for the sentence that will gentle the paradox. Einstein in white chalk, making time stand still long enough to test a thought. Heisenberg returning from Helgoland with hay fever and a new mechanics. Dirac, quiet as a moonbeam, inventing antiparticles because the equations asked politely. Over it, a newer reel. Interferometers catching whispers of gravity. Cat qubits lounging in cavities. Entangled satellites passing secret notes across night skis. You take a seat where the carpet's thicker and the talk blurs into a murmur. You realize every position here picks a sacrifice. Locality or determinism, single world comfort or branching honesty, collapse as mechanism or as myth, reality as stuff or as story. There's no free dessert menu. You pay for sweetness with something you thought you needed. The room doesn't mind. It's been open 100 years. It will pour 1 more cup and keep being friendly to the next person who wanders in with a pocket full of paradox. On your napkin, you doodle your own mini interpretation. Half cat, half compass, a little wave, a little particle with an asterisk. For now. The bartender refills your water as if that's the best answer anyone given all evening. When you stand, the door at the back is already ajar. Beyond it, the lounge's amber dwindles into deep blue. You glimpse scales shifting, plank to planetary, atom to archipelago. The conversations behind you fade to a comforting buzz, like an old radio left on in another room. Whatever the right story is, the universe outside has been telling its own for 13.8 billion years without waiting for your footnotes. You slip through, carrying a handful of callbacks, Planck's pixel, the amphitheater's zebra, the cat's flicker, the uncertainty blanket, the entanglement bracelet, and feel the floor tilt toward a wider, softer horizon. The next room smells like night air and starlight on metal. Time to zoom all the way out, just to see whether the small and the vast still rhyme when the lights are low. The deep blue ahead spreads like an ocean you can walk on. The air feels bigger here, less like something you breathe and more like something you're floating inside. The floor is smooth, reflective, mirroring a starfield so dense it's hard to tell which way is up. You've left the cafe's amber warmth behind, stepping into the sleepy cosmic zoom out. You start small, very small. In your hand is a single electron, the kind you met back near the beginning, back when Planck's constant was a rope bridge and the double slit was still fresh gossip. You imagine its wave function, soft, blurry, probabilistic, woven from quantum field ripples. You take a step back and the electron becomes part of a hydrogen atom, the simplest little system, a proton holding court at the center while the electron's cloud swirls like patient weather. Step back again, and now you're in a molecule, atoms dancing to quantum choreography, bond lengths, orbital symmetries, vibrations set by the same uncertainty principle that kept your toes warm in Section 6. Chemistry itself is quantum writ politely, its rules distilled into recipes by people who didn't know they were following wave functions. Mainstream history hums along. The first image of an individual atom came in 1951 via field ion microscopy, and scanning tunneling microscopes in the 1980s turned atomic landscapes into something you could navigate like a city map. In the decades since, manipulating atoms one by one has become routine, writing initials in xenon on nickel, assembling quantum dots, trapping ions like songbirds in tuned cages. Historians still argue whether the public really grasps that every table, chair, and cat is, deep down, composed of these dancing quanta, or whether quantum has been so overmarketed as magic that the ordinary miracles get lost. You take another step back. Now you're looking at grains of dust, specks of pollen, your own fingertip, macroscopic, sure, but still anchored to the probabilistic stage underneath. You can almost see decoherence happening here, fast and ruthless, blurring the interference patterns until everything behaves classically. And now the zoom accelerates. Your fingertip becomes part of a hand, then a person, then a street lit by sodium lamps, then a spinning Earth with its superconducting planetary core and magnetic shield, both with quantum signatures if you squint. Step again, and you're looking at the moon's orbit, the gravitational sling of planets, the faint tug of relativity shaping trajectories. Joke number 1 drifts up. We're all just quanta in very slow motion, pretending to be furniture. You're far enough out now to see the solar system as a clockwork of planets, moons, and comets, classical mechanics in the driver's seat, but the gas in the tank still quantum fusion inside the sun. Another step, and the Milky Way spills across your field of view, 100 billion stars each with their own quiet double-slit experiments happening in electron shells and nuclear cores. In the far distance, filaments of galaxies stretch like the quantum field quilt you walked across earlier, now embroidered on a scale so huge it takes light billions of years to cross a single thread. The cosmic web hums in microwave static, the afterglow of the Big Bang, its temperature fluctuations tiny, but mapped with exquisite precision by satellites. You remember that even these patterns trace back to quantum fluctuations in the universe's first instance, stretched by inflation into the seeds of cosmic structure. A quirky tidbit flickers in your memory. Those ancient fluctuations are the largest quantum events we can observe, painted across the sky. Every cluster, every void, every spiral arm in every galaxy carries the imprint of microscopic jitters blown up to intergalactic proportions. Joke number 2 hums, quantum mechanics, proving that even the universe started with a case of the jitters. You step so far back that the galaxies themselves become dots, then threads, then a fog of light. You're at the edge of the observable universe now, 46 billion light-years in every direction. The horizon is not an end, just a limit set by light's long commute. Beyond it, maybe more of the same, maybe something stranger. Cosmology stops pretending to be certain. Historians still argue whether the multiverse is a respectable prediction of physics or just an extrapolation wearing a lab coat. Inflation's equations make room for it. Many worlds suggests it in a different key. String theory adds its own sprawling landscape. You can't see those other realms from here, but the silence is suggestive. You turn slowly, letting the stars wheel beneath your feet. Every step inward from here back to the smallest plank-length loops is the same story told at different scales. Patterns, interactions, probabilities, and the quiet, stubborn constants that keep the whole performance in time. Quantum mechanics isn't just down there in the basement, it's the wiring in every floor of the building. Joke number 3 strolls in for a curtain call. The universe is the longest-running play in history, and quantum been the stage crew the whole time. You let the zoom slow, your perspective settling somewhere between molecule and moon, where the air smells faintly of both chalk dust and rain. All the sections you've wandered through, Planck's tiny constant, the cat's nap, the interference zebra, the entanglement bracelets, the vacuum's quiet hum, fold themselves into a single, sprawling panorama. The world is stranger than your instincts wanted, but calmer than your fears suggested. You close your eyes. Somewhere nearby, a particle hums in sewer position. Somewhere far away, a galaxy swirls. Between them is the same physics, running without hurry, without pause, waiting for you to wander back through the door and pick up the story again. Word count, 1101. End of script, sweet dreams.